Good day, students. In this group, we're going to be going over how to prove the moivre's theorem using mathematical induction. Okay? So, all right, before we start with the proof, let's go ahead and go over the plan for induction real quick, and then we'll go over some prerequisite formulas that we're going to be using in this proof. Okay? So this is the plan for induction, basically. So first of all, we want to show that the base case is true. So we start with the base case. Base case. For the base case, we just want to show that the statement is true. The statement is true for n equals a. Okay, a is the initial case where the statement holds for. In most cases, it starts from 1. In some other cases, it could start from 0 or maybe any integer. Okay, so base case, show that it's true. The statement is true for whatever the lowest constraint is for n. And then 2, we have to make a statement which is known as inductive hypothesis. Inductive hypothesis. In the inductive hypothesis, we're just going to assume that the statement is true. So assume the statement Sn is true for n equals k. Okay? So assume that this is true for any arbitrary k in a set of integers. Then if we can show that in step 3, known as inductive step, if we can show that truth for Sn, the inductive hypothesis implies true for the next step, sk. If we can show that true for sk implies true for sk plus 1, then we're done. Okay, so you see we're setting up like a domino here. This is the foundation of the domino, the first case. And if we pick any arbitrary n, and if we show that truth for that n follows that the next is true, then that pattern carries on forever. Okay, that's the beauty of the mathematical induction proof. It's just like a step-by-step process. Okay? All right, so this is the plan of attack that we're going to be using to execute our proof. But before we start, let's go over just 2 formulas that I'm going to be using in this proof. Prerequisite knowledge. You just need to remember your trig identities, namely the sum identities for sine and cosine. So just remember that sine alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. Okay, remember addition commutes. Multiplication commutes, so these can become in any order and it's still the same thing. Okay, all right. And also the sum identities for cosine, we're going to be using in this proof. Cosine alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. Okay, so these are the 2 proofs I'm going to be using, 2 identities I'm going to be using in this proof. Okay, all right, let's go ahead and do the proof. Okay, so what we're going to prove, we need to write down what the statement is. So Sn, the statement Sn, we want to prove that the statement Sn, which is r times cosine theta plus I sine theta, this complex number in polar form raised to the nth power is equal to r to the n times, let's put in this format, times cosine n theta plus I sine n theta. Okay, so this statement we have right here for all, let's write down for all n greater than or equal to 1. So this statement that we have right here is the moivre's theorem. Okay, and this is what we are going to prove. All right, so let's go ahead and do this proof. So part 1 is our base case. Okay, base case. So for our base case, what we're going to do here is, let's put what we want to do in parentheses. There are 2 ways of writing it, okay? I'm going to write them both ways so you can see. So we want to show, this is a shorthand way, show that S1 is true. Okay, this is one way of writing it, or you can write it, show n equals 1 is true. All right, so you can write it in this way, show that S1 is true, or show that n equals 1 is true. Any of these methods will suffice for the base case. Okay, so I'm just leaving flexibility here for you to construct the proof in whichever way you like. All right, so we want to show that S1 is true. So what we're going to do is plug in 1 into the statement and see if we arrive at an equivalent equation, an equivalent statement. Okay, a true equation. So on the left side, I'm going to plug in 1. I'm going to have R times cosine theta plus I sine theta raised to this complex number in polar form raised to the first power. Is it equal to what I'll get here if I substitute 1? That's the question. Okay. All right. So let's simplify this and see if I can transform this into this format right here. All right. Now using the product property of exponents, I can distribute this power to this product in here. Okay. So we're going to have R to the first power, distributing this 1. See this 1 right here? I'm going to distribute the 1 to the R, and I'm going to distribute it to this entire quantity right here. Okay? So if I do that distribution, I'm going to have R to the 1 times cosine theta plus I sine theta to the first power. Okay? All right. Now, R to the 1, I can just leave as R to the 1. And now cosine theta, if I raise cosine theta plus I sine theta to the first power, is just 1 copy, so I can drop the 1. But I can also factor out a 1 from here, so I can write this as 1 theta, 1 times theta, plus I, I sine 1 times theta. Okay? And guess what? We have this form just like this. Okay, so this shows that the base case is true, because when I raised this whole expression to the first power, I had the radius raised to the first power, and I could factor out 1 from the thetas raised to no power at all. So this is exactly what we have. So base case, we've been able to show that the statement is true for n equals 1. Okay? All right, now let's go ahead and state do our inductive hypothesis. That's step 2. Okay? All right, so 2 is our inductive hypothesis. Inductive hypothesis. Okay? All right. So for inductive hypothesis, remember what we said before, we're just going to assume that S of k is true. Okay? The 2 ways of writing this, I'll show you both methods. You can pick any one you like. So the first way you can write it is you can say, assume S sub k is true. This is one way of writing it. Or if you don't like that, you can write assume n equals k is true. These two statements mean exactly the same thing. So any format you like, if you like the subscript method, go ahead and do that. If you want the if you like this complete statement method, you can do that also. Okay? All right, so let's go ahead and make our inductive hypothesis. Now this is how you construct an inductive hypothesis. You simply restate the original statement, replacing the n's with k's. That's all that there is. Okay? So I'm just going to restate this original statement, replacing the n's with k's. Okay, so we're going to write the following statement. Assume that S of k, which is basically R times, write this part properly, R cosine theta plus I sine theta raised to the kth power. We're going to assume that this is equal to R to the k times cosine k times theta plus I sine k times theta. Okay? So what did I just do here? I just restated the original statement, which we're supposed to prove, use replacing n with k. Okay, for assume that this statement is true for all n for all k greater than or equal to 1. Okay, so that's basically how you do your that's how you construct your inductive hypothesis. Okay, all right. Okay, now that we have our part 2 down, we're now going to go into the heavy lifting, the inductive step. Okay, now let's write this down. The title, inductive step. This. All right, so let's write down the title of part 3. So 3. This is the inductive step. Okay, we've picked an arbitrary point in the set of all integers, and we assume that that is true. So if we can show that the next integer is true, then we've been able to accomplish our goal. So we can conclude that this statement will hold for any integer greater than or equal to 1. Okay, so inductive step, for that one, we're going to show two ways of writing this. I can just write it. Let me write it in the shorthand way. So I'm going to show true for s sub k implies true for s sub k plus 1. Okay? So if I can use this inductive hypothesis within this next step to show that the next step is true based on the fact that this is true, then I can conclude that my proof is correct. Okay, my statement is correct. Okay? All right, so showing true for s sub k implies showing true for the next step, then the proof will be complete. All right, so what I'm going to do is I'm going to start with the next step, which is s sub k plus 1. So I'm going to start with the left side of my statement, and then I'm going to take a step. Okay, so let's take one step forward on the left side, which is going to be, remember, we want to show that s sub k is true using the fact that we want to show that s sub k plus 1 is true based on the assumption that this is true. Okay, so taking a step forward, the left side of s sub k plus 1 is going to be r cosine theta plus I sine theta. Since this is raised to the kth power, the next step we're going to be raising it to the k plus 1 power. Okay? All right. Now what we're going to do next is as follows. Okay, so the goal is to show that now that we've substituted k plus 1 on the left side, can I arrive at a statement where I have the right side of my statement expressed using k plus 1. Okay, so if I can arrive at that situation where you see the right side of this equation is written with k plus 1 instead of k, then I would have shown that the statement is true. Okay, all right, so let's work with this side and see if we can arrive at a statement that looks like this, but with k plus 1 instead of k. All right, so this is what I'm targeting here, just to help you see. See this k's right here? I want them to be k plus 1. That's the goal. Okay, because I changed this k. You see this k right here? I changed it with k plus 1. So I want to see if it transforms into a situation where I have this right side with k plus 1 substituted. All right, so let's go ahead and do that. So now let's see. First I'm going to use the reverse of the product of powers property. Remember the product of powers property, when you multiply two powers, you add the product. And when you multiply two powers, you add their powers, as long as the bases are the same. So using the reverse, if you have the sum of two powers, is the same thing as the product of the respective, the power of the respective products. Okay? So that's what we're going to be working on right here. So I'm going to do the reverse of the product of powers property, and I'm going to split this. I'm going to split this power into this and this. Actually, before I do that, I'm going to use the following. Yeah, I'm going to use the power of products. Yes, power of products first before I use product of powers. So I'm going to use the reverse of powers of products. Okay, so if I use that, the reverse of that, I'm going to distribute this. See this power right here? I'm going to distribute it to this quantity and to that quantity right there. Okay, so basically it's going to be, we can rewrite this as r to the k plus 1 times cosine theta plus I sine theta raised to the k plus 1. Okay? So if you look at this expression I have right here, from right to left, if you remember your product of powers property, whenever I have the product of powers, is the same thing as you can factor out the powers from the product and express it in this form. So I just use the reverse of that idea to have this expression. Okay? Now that we've used the product of powers, now we're going to deal with the power of products property. Okay? So this right here, if you see this sum of powers right here, whenever you have a product of powers with the same base, you can express it as a sum of their powers. Okay, so what I'm going to do is I'm going to use the reverse of that to break this exponent down and also to break this down. Okay, so this can be written as a product of powers. So this can be written as r to the k, let's switch the order, r to the 1 times r to the k. Remember your product of powers property. Let me just write it on the side here. You have a to the b x times b to the a to the x times a to the y. Okay, a to the x times a to the y. What does this become? This becomes a to the x plus y. Okay, this is the product of powers property. You add the powers when the bases are the same. Okay, so that's what I did here. I did the reverse. I started from here and I went backwards. So I split this up, because if I multiply these together using this property, I'll end up with that. Okay, so I'm going to apply the same idea here. Okay, I'm going to express this as cosine theta plus I sine theta to the 1 times cosine theta plus I sine theta to the k. Okay, so this is also the product of powers formula. The bases are the same, so you just add the exponents, right? That's exactly what I did here. So now we're going to use the commutative property of multiplication to reorder this expression in a way that we can create an opportunity to substitute our inductive hypothesis or assumption. Okay, so what I'm going to do here, I'm going to reorder them. I'm going to extract the powers of 1. I'm going to write this as r times cosine theta plus I sine theta, and then moving this to the left of this, to the right of that, I'll have r to the k cosine times cosine theta plus I sine theta raised to the k power. Okay, now using the power of a product property of exponents, we're going to make the following substitution. Yeah, so let's just focus on this side right here. Okay, so let's focus on this side. I'm going to put this thing right about that. Well, so I'm going to focus on this left side right here. I'm going to use the power of a product property on the left, because you know the bases are different. Okay, so we have this. I'm going to see the powers are similar. I can factor that power out. Okay, just like the reverse of what we did here. So we'll bring down the left side. We're going to have r cosine theta plus I sine theta times r. Let me write this in a different color so that you can zoom in on a critical component that I'd like you to see. So I'm going to write this in green. So after factoring out this power, I'm going to write this as r cosine theta plus I sine theta. Close that. And then we're going to close the entire parenthesis. Let's see, close that, and then we close this. To the k power, we just use a power of product property, the reverse, to generate this idea. So now, check this out. This expression that we have right here, r cosine theta plus I sine theta to the k power, what does that look like? What does this expression that we have here look like? That's a question. So let's just zoom in on this piece right here. What does that look like if you focus in on that? This thing that we have highlighted right here is similar to the left side of our assumption. Since this is the same as the left side of our assumption, guess what? Since we assume that this is true, this statement is true, we can substitute the right side with this term right here. So I'm going to substitute the right side of this statement with this because this matches with the left side. So I'm just going to replace the right side with this statement here. Okay, so based on our assumption, we can accurately state that this equation is equal, and move it a bit to left a bit because it's going to start getting long now, is equal to r cosine theta plus I sine theta times, now I'm going to rewrite this in a different color so we can focus in on it. I'm going to write it in blue, times r to the k times cosine k theta plus I sine k theta raised, oh yeah, just that. Okay, so where on earth did I get this from? This is the right side of my inductive hypothesis, remember? Okay, so I just made that substitution here using our inductive hypothesis. We said that this is equal to that. We assume that that's true, okay? So there you have it. Okay, now looking better, we're going to try and see if we can make this look like the right side of our inductive hypothesis with k plus 1 substituted instead of k. Okay? All right, so what I'm going to do first, I'm going to use the commutative property of multiplication to regroup my terms here. So I'm going to write this as r to the 1. I'm going to commute this r to this right here, r to the k. And then times cosine theta plus I sine theta times cosine k theta plus I sine k theta. Okay? All right, so what we're going to do here is just FOIL it out or distribute, whichever way you call it, these two trig expressions in parentheses right here. Okay, so let me show you what I'm about to do. I'm going to go first, outer, inner, and then last. Okay, I'm just going to distribute. That's all I'm doing right now. All right, so let's go ahead and do the distribution. When I do the first distribution, this two right here, using the product of powers property of exponents, if you have the product of two exponents with the same base, you can write this as a sum. So I can write this as r to the k plus 1. Okay, leave that alone because it's perfect. That's exactly how I want it. Now let's distribute here. We're going to have cosine theta times cosine k theta. That's the first. And then outer is going to be I cosine theta sine k theta. Okay. And then first outer inner is going to be plus I sine theta cosine k theta. Uh-oh, I'm running out of space. And then plus, when I do the last one, is going to be I times I square sine theta, so I square sine theta sine k theta. Okay, so that's what you have, close the parentheses. All right, so just by distributing, this is what you get. Okay, so let's go ahead and simplify our product. So we're going to have r to k plus 1 times cosine, let me reorder this, okay? Using commutative property of multiplication, I can write this as cosine k theta, cosine theta. Now remember what I square is. Remember I square is what? I square equals negative 1, right? Okay, so I'm going to replace this positive I squared sine theta sine k theta with negative. This I squared changes this plus to a negative, minus, using the commutative property of multiplication, I can reorder this as sine k theta, sine theta. The order doesn't really matter when you're multiplying. Plus, now I can factor out this I from these two middle terms, okay? Factor out the I, and I'll be left with, let's reorder these two. Sine k theta, order of multiplication doesn't matter, cosine theta, plus, reorder this also, cosine k theta, sine theta, okay? All right, what do we have here? Well, what we have here, close that, and then we're going to close. Let me just do my regrouping because I'm doing multiple nesting here. So the outermost one, let me use a squiggly bracket. Bam, like that. Okay. And then I'm going to have a squiggly bracket somewhere out here. Anyway, so my grouping right here, let's do this so you can see it clearly. I'm just going to move it to the left a little bit. Okay, so let me redo the grouping structure so you can see it clearly. You're gonna let me see. So I sin theta, so we use a bracket to close that, and then use a squiggly bracket to close off the entire thing. Okay, looking good now. Okay, now so what we're going to do is look at what we have. If you look closely at what we have, this is just exactly what the some identities I showed you earlier is, isn't it? So cosine, 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 sine, sine with a minus in the center. That's exactly what we have here. Cosine alpha, cosine beta, sine, sine. So guess what? The first expression, let's leave this alone, r to the k plus 1, is a some identities for cosine, right? So I can write this as, squiggly bracket, cosine, cosine of the sum of the angles. This is like an alpha, and this is like a beta, right? And this is like an alpha, and this is like a beta. So it's going to be cosine alpha plus beta, okay? So it's going to be cosine k theta plus theta. This whole expression right here, this is the condensed form using the sum identities for cosine. All right, plus I. Now, if you look at what we have here, this is the sum identities for sine. Sine alpha plus beta. Because you have sine, cosine, cosine, sine, alpha, and beta. Yes? All right, so there you have it. So this is going to be plus I bracket sine parenthesis k theta plus beta. Okay? And then close that up. All right, now to finish this up, we're just going to simplify the arguments of our trig functions by factoring out the common term. Okay, so this is going to become r to the k plus 1, squiggly bracket, cosine, let's put a bracket here, k, I'm going to factor out theta, okay, because that's what's common in both of them. So if I factor out theta times theta, if I factor out theta from these two, I'll be left with k plus 1 times k plus 1, like that, okay, plus I, bracket, sine, factor out theta from here also, bracket, theta times k plus 1. Okay, close that bracket, close the bracket, and close the squiggly entire expression. So guess what? We have accomplished our goal. We've been able to write this in the formulation where our assumption has all the k's in our assumption has been replaced by k plus 1. So by mathematical induction, we are done. Okay? So we can just write a closing remark since S of k implies S of k plus 1. Statement is true. Okay, the statement is true. It's true. Okay? This is proved by mathematical induction. We could put a box of accomplishment. Alright, so there you have it. So thanks so much for taking the time to watch this presentation. Please feel free to subscribe to my channel by clicking up here. I really appreciate it. If you like this video, you can click like and post a comment to tell me what you think about this presentation. And more videos can be found on mathgotserved.com. Thanks again and have a wonderful day.